Good evening, ladies and gentlemen. So first of all, I would like to thank for the invitation and for the honor to be there tonight with you. I would like to share some experience about resilience. I will come back to the field and to the reality of resilience. It's a bit about the experience I had during the last, I would say, 10 years. Through various projects, which are related to water, obviously, but also regarding the management of cities. I had the chance to participate to several projects supported by the European Union taking place obviously in Europe, but also in various places in the world. And so we had with some colleagues to face this challenge of resilience and to try to define what is resilience and how to come with operational tools. So I think the presentation from Karen was very nice regarding the big framework. I will really come back to the reality of the things and trying to see how we can bring operational solution. I hope in the room there is some urban planners, engineers from technical services, from municipalities or decision makers. Message is for you. So you are free to disagree with me. I will be very happy to discuss with you and to see how we can move on. Before we go to the reality of the things, I think it was stressed in the previous presentation. We are facing a very unique situation in the world. Obviously, we get a majority of population now living within the cities, but at the same time, we have a new shape for the city. So the shape of the city is something we have never seen in the past. Of course, we had in the past cities with 1 million inhabitants. That was the case about Angkor. Angkor was one of those cities deeply affected by climate and so on. So they had 1 million inhabitants before to suffer about water, drought, and so on. But currently we have cities with a huge density, a huge quantity of population. So it means regarding technical issues and also for managing the society, we are facing real new challenges. I just pick up three pictures. So this one is from Mexico City. So which is something which is quite interesting. See, if you never landed in the city of Mexico, you have really the feeling when you are going to the airport, so which is in the middle of the hills, you are fully surrounded with houses everywhere. So you know it's like a carpet, you know. So it's growing and going over the hills. And so obviously for urban planners, it's a real nightmare. How could you address that? How could you provide water? How could you provide energy? How could you organize traffic, public transportation, and so on? So this is really one of the most important challenge. At the same time, you may have such a type of very nice environment, so which is Hong Kong. This is Kowloon. This is also a place where you get a very interesting density. Many of those towers going up with very teeny apartments, huge density, and also with very interesting problems regarding water supply, regarding electricity, regarding health. If you remember, this SARS event was related to this quality of sewage system, which was not really appropriate in those towers, very cheap to build and so on, but not always with the fine technical requirements in order to avoid such a type of problems. And obviously, we have also other situations which are quite interesting, where we have this challenge to bring, I would say, what we like regarding cities. I would say modern comfort, the pleasure to enjoy a nice garden and so on, in an environment which is maybe not fully dedicated to have this type of urbanization. So this is from the US. Obviously, this is not from Canada, not yet, I would say. I hope that will be never the case, but anyway, so this is some of the challenges, just to say this is the reality of the things we are facing. I think it was said already, the world will be covered with cities. This is one of the projections you have on the screen, which is showing how the world populations will grow in the coming 20 years. And obviously, you see that this density is growing up in different parts of the world. We are currently in Montreal, in a place which is supposed also to know a significant growth regarding cities, but it's obviously not fully covered everywhere, and we have some challenges. I would like just to focus a little bit on Europe. I'm coming from France, so it's quite obvious for me that I have to speak about Europe at least, not talking about France. And what you see over there, so it's just a picture, so which is coming from our German colleagues, so where you can see the density of the network, density of cities growing, especially in the north part of Europe, Netherlands, Belgium, Germany, and also north of France. And you see this density of cities and different networks which are growing. Of course, as it was mentioned in the previous presentation, we are supposed to be affected by climate change. I just picked up this document from the European Environment Agency, which is making the long list of the potential impacts that we may have in Europe. And you see this is really, really a long list. It starts from Arctic, where we have problems regarding temperature rise, reduction of permafrost, impact on the various things, as it was mentioned by our colleagues. And of course, for the west part of Europe, it remains, I would say, more comfortable, no big impact. But for the Mediterranean regions, we are supposed to have a long list of impacts starting from temperature rise. Of course, decrease of annual precipitation. That's the case, but I will show you an example in a minute that you will see exactly the opposite, that we are facing quite important increase of precipitation in some local places for different reasons. Increasing of risk regarding diversity loss, increasing of risk of desertification, increasing risk of forest fire, and so on. So this is almost an endless list of potential impact, which is supposed to affect most of the Mediterranean regions. This is also the case for Central Europe. There is also consequences. So it's just to say this is something which is already a reality. Europe has invested massively during the last two research frameworks supported by the European Union during the last 10 years for having analysis and trying to integrate those elements and to develop policy and to mobilize population, but also municipalities in order to act and to implement solutions. If we try to understand and try to give some example, I would like just to use two examples which have been observed in France recently. So what you have on the left part of the screen is one, I would say, unfortunately famous storm. So we had in 2010, which is called Scindia Storm. So which is almost like a hurricane. This is what you are facing on this part of the world. It was something which was fully forecast. So the meteorological services did a nice job. I would say 3 days ahead. It was perfectly known. The storm was coming, was defined properly, intensity and so on. So the problem was that everybody was expecting that most of the coastal defense will ensure an efficient protection. That was not the case, you know. So we design in Europe a lot of coastal defense in time. So it means it was made, I would say, 1-2 centuries ago, and we are facing right now a very interesting problem, so which is maintenance. You know, European economy is not so high. Economy of various states is not at the highest level, and maintenance is becoming a real issue. And in that case, what you see over there, so which is a situation about Charente-Maritime, close to La Rochelle, on the western part of the Atlantic Ocean. So we had a lot of breaks on the different levees and protection which have been over there. And most of the places which were behind were supposed to be protected by those embankments have been flooded. 47 people died, just because they were aware about the situation, but they thought we were safe because we are behind the dikes. And so this is one of the main problems we face is in this situation. What you have over there is just a simulation which is showing how much the land was flooded and how this storm surge was affecting the coast. And this is something which is a very serious crisis and which was even supporting the development of a new policy. So we have created in the French law, in the French regulation, what we call black zones, where we are destroying houses. So we are not allowing the people to rebuild, but we are destroying those houses, knowing that no one will be allowed anymore to build over there, and no protection will be reintroduced because we do not have the capacity to support the cost of those protections. So it means we are not anymore in the stage of trying to protect. On the other side, so you have another example, so which is in Nice. So we had in 2015 a very intense storm. So when I say intense, it's something which is really exceptional. So I was just discussing during the last 2 days with the colleagues in Montreal regarding the extreme rainfall you're having here. So we had 200 millimeters in 2 hours. Okay, so it means with those values, so this is what you have on the video, so everything was flooded. So all defenses were completely overtopped. Everything was flooded, including parking lot and so on. And during this event, 21 people died. Most of them, I would say 18 over the 21, were just dying due to the fact that they were not behaving properly in this situation. Most of them were trying to go in the parking lot to rescue their cars. Okay, 18 people die for their cars. So which is, I would say, you can do a lot of efforts for protecting the people and so on, but if you don't bring the sufficient information, sufficient education, how to behave in such a type of situation, you cannot avoid such a type of things. And so this is something which is really important for engineers. It's nice to do protection, but how do you communicate efficiency of those protection? I would like to move to some of the extreme events which are also very well known at the worldwide scale. Of course, it's not directly related to the climate change, but what you have on the left is the tsunami in 2011 in Japan. And what you see at the front is just this protection wall, which was supposed to be efficient for 1,000 return year event. So it means people behind were supposed to be safe with these infrastructures and not being flooded. We had more than 2 meters above this wall. So it means even with a very strong protection made at the top of what we know regarding the different processes, that was the consequences. On the right side, you have something which was closer to you. So it was about Sandy. Sandy was even affecting McDonald's. You know, even McDonald's is not fully waterproof and was affected by this story. More seriously, it was a very interesting list of failures, especially gates and doors which were supposed to be closed in the subway, in the different infrastructures, which were not operating, just because the people have realized that those doors cannot be closed just if the electricity is not operating anymore. So this is the kind of things you cannot invent, but this is the things you realize at the very beginning when the crisis is coming on, and this is something which is really important to understand. So just to summarize those elements, so what are we learning from that? So in fact, we are learning that vulnerability of our cities has increased due to the fact that we have a higher density, more people living in. We are more complex. We have more and more services, facilities, infrastructures, which are sensitive to climate, obviously, but which are also sensitive to major crises that could be related to flooding, earthquake, or whatever it is. At the same time, so we need to combine protections with preparedness, awareness, and adaptation. So this is what is requested. Of course, on the left, you have this image about Japan. The coast has been fully submerged. What you have on the right is a big flooding that we had in Bangkok in 2011, so which was in September. It was supposed to be fully organized regarding the rescue teams. Everyone was supposed to use those highways, which are clearly above all the city, but unfortunately, the people were using those highways to save the cars. Once again, I mean, when the flooding was coming, everyone was using those highways to go and to park the cars, which is meaningful. I mean, so you want to say what you have in your hands, so the best way was to park the cars over the highway, and no rescue teams were able to reach the people who had to provide food and support. So this is the things that have to be thought before and to try to implement in the management of the cities, and this is something which is quite challenging. So this one is really impressive and is just trying to explain clearly for those who are making the design, be sure that your protection will fail. This is something which has to be taken into account. As I told you, it was supposed to resist for 1,000-year return period events. We had more than 2 meters of water above the wall. And obviously, it was fully affecting the story, and this is what we need to do now. So one of the very important changes after this event in Japan was to try to reintroduce new concept in engineering, try to investigate what if. So we do the design, we assume we have sufficient level of protection, but what will happen in case we have this situation? And in fact, the resilience concept is something that could be used for addressing this principle. I was trying to look a little bit to the definition of resilience, because it's something which is very trendy. Everyone is using the resilience. I'm not so sure that the definition behind is the same for everyone, even in the room. And if you look back in the situation in the last development, so you see that the most frequent references came at the beginning of 70s, and it came from the biologist community. So this is the definition you have on the screen. And this is just describing ability of a system to absorb disturbance and to regenerate afterwards, to come back to something which is close to the previous state. Of course, you had various changes, a little bit of different inputs from various authors trying to explain self-organization, how much the capacity of learning and adaptations. This is things which are now fully integrated. This is also something which has been used by social sciences, especially in France. We have a psychanalyst who is working on social resilience and who is very famous. And so that's why I just took this example from the city of Paris. Of course, there is a strategy for the resilience, which is regarding infrastructures, but also regarding the social dimension of the resilience, how to increase social link and how to increase solidarity among inhabitants and the different components of the society. Currently, there is one definition, and I would prefer to stick to this one, which was produced by the UNISDR in 2017, which is the latest one, so which is just explaining how a system, a community, or society may recover after one hazard and how it could come back to a kind of normal actions. I was just looking yesterday on the number of references about resilience, 57 million of references in Google about resilience. So there is, I think, a little bit of work to do in order to be sure that everyone is addressing properly this concept. Engineering is not the most important part in those references, so there is space. So dear colleagues, if you would like to invest a little bit more in that field, I think that will be strongly beneficial. So this is a multi-dimensional, and this is an integrating system. If you look at the literature, and especially in engineering, what you find is basically this concept. So, and in this concept, there is a confusion between resilience and elasticity. Because if you look at the graph itself, so here we have the disruptive event, so that could be earthquakes, that could be flooding, that could be tsunami, whatever you want. And then you have a first impact on the society, on the city itself, which is supposed to go to a minimum and then start to respond, recover, and restore. So this is basically how we assume the things. How deep we go, it's how much vulnerable we are and how strong are our resistance infrastructures we have created. Obviously, all the engineers have in mind to reduce impact of one of those events and to have a less deep impact, reduce the vulnerability, improve the situation and the capacity to recover. And so what we are trying as engineers most of the time is trying to minimize this distance between the two things. The problem in this concept is that we assume that we are supposed to come back to what is frequently defined as steady state. We assume we are going to come back to the previous point to recover and to regenerate the things. In fact, this is not true because you may have those different lines. So first, you may continue to go deep. So it means it may go so bad that you cannot recover afterwards. And I think it was the example of the various cities which have been deeply affected by the climate change. This is the case of Angkor in Cambodia. The city was so strongly affected that the city was never able to restore afterwards. So then you may have a partial restoration. For me, this is exactly the example of New Orleans. New Orleans are still not fully recovered following Katrina. So this is not the case in all cities which are affected by major things. You may come back to the previous state, but you can also improve. So this is something which is really important. From the crisis, you can learn and you can adapt and you can recover better. You can do a better environment. There is a very famous example, so which is a big fire in London, 1666. 3 days of fire, almost more than 13,000 houses which have been burned during this period. Almost 70,000 inhabitants which have been affected. So it's almost more than 80% of the people who have been affected by this important fire. Consequences have been extremely important for the city. First, the city has been rebuilt. You see a new organization, not anymore with wood, but with stones. So it means we have improved the quality of the buildings, the quality of the services provided to the population, and something which is really interesting and exceptional is that the last bubonic plague was observed the previous year, not anymore after this big fire and the restoration of the city. So it means from the crisis itself, you may arrive to a better situation, and this is maybe the way to cultivate hope together and to try to see how we can improve the society. I would like just to finish on this aspect with a kind of graph which is just showing the global resilience, how we may describe the global resilience. In fact, we may assume that we have this growth of the resilience for cities. We may say that the resilience started to decrease due to the fact we have introduced more sophistication in our cities, more people were coming to live, but we have a continuity of this growth and a combination of small disruptive events. And so it means at each time we are improving, we are adapting the capacity of the city, and this is what we have to figure out and to see how we can avoid to go so deep and to try to move on and to arrive to a situation where we improve the quality of the resilience of our cities. As I said, when we have to face the challenge of new urban environments, there is two different attitudes. Obviously, one of the things is to try to go for structural protection. This is a normal attitude for engineering. Most of the engineers have been trained to have stronger walls, bigger pipes, new pumping station, and so on. That's nice. But unfortunately, for extreme events, those solutions are not always efficient. I think it was clear in the previous example I gave. So if we look on how we combine and we define the things, the objective most of the time is to have protection measures, so it's structural measures, and we try to reduce impact. This is the general philosophy of the things. But now if we introduce resilience, we may have a different curve. So what we want to reduce damages. Resilience could be information to the population, could be alternative solution, alternative technical solutions that we may introduce. This is also non-structural measures that may help to improve the security of the population. So in that case, we may arrive to a situation that we may discuss the level of protection we introduce. And so this is something which is quite challenging for the engineers. Up to now, everything was defined for having a protection level which is 100 years. Why 100 years? Why not 75? 75 would be nice also. If we accept to be flooded with a more frequent situation, but if we have a perfect knowledge about how we will be flooded, how we will be affected, and how we will adapt, we may move to this approach, reducing investment, reducing maintenance cost, obviously, and having a more active and proactive resilience measures implemented within the city to the communities in order to be ready and to adapt. I just showed the pictures about Bangkok. Bangkok was flooded almost for 3 months in 2011. 3 months after this major flood. So when I say major flood, it was about 2 meters downtown. 3 months after, the full city was operational, which is absolutely not the case of New Orleans after so many years. So it means more flooded you are, more resilient you are, and more ready you are to adapt and to improve the things. Now the question is, how could we quantify it? I mean, so I'm pretty sure if there is some practitioners in the room, they would say, okay, this is nice, but how could we implement those things in a very operational way? And how can we bring those measures? The problem came up during one project we did with our colleagues in China and for the European Union. So we had a very simple problem, which was, how could we define a city? Okay, it's nice. It's a nice problem. We have a definition in France, so, which is in fact related to the distance between buildings. If you have less than 200 meters, you are in a city. If you have more than 200 meters between buildings, you are not in a city. Okay, that's nice. I said that to my colleagues in Beijing, and they say, oh no, for us it's much more obvious. Below 1 million, you are not a city. Okay, simple. So we came to a pragmatic definition, and I'm sorry if there is some urban planners in the room. I'm just an engineer, hydraulic engineer, so I don't want to fight with you about the definition of a city. But we came to a very basic definition, which was to say, in a city you have two types of things. You have urban functions. Urban functions are associated to buildings. So it means when you look at a building, you can say this building is dedicated to governance. This is an hospital. This is a school. So you can give a function to those buildings, and you can say this is used for working, this is a residence, and so on. And in order to operate the city, you have services. You have only 5 services, which are transportation, which are water, which are communication, solid waste, and energy networks. With those 5 networks and those 9 functions, you can describe the city. It works in Europe, it works in Asia, works also in North America. So if now you try to assess and to look at those functions and service according to various scales, so you can look at the parcel scale, individual building, but you can also look at the block, to the district, and to the city scale. You may try to have a global mapping of the city and how this city is working. When you can describe how the city is working, you can see, you can try to define how the city is affected in case of a crisis. Is it a heat wave? Is it a shutdown on the water supply, and so on? So you can give some indexes, some marks, and see how much you could be affected. So I would like just to share with you one application which was made regarding flooding. So the principle was applied to various locations. It was made in China, it was made in China, in Europe, obviously. And we try in a very simple way to give a mark from 5 to 0. 0 means you do not have this function available. You cannot stay in your home. 5, you are not affected, so you can stay, you can continue to live in your apartment without any problem. And of course, you can define in between different marks. If now you look at the different services you need to stay in your house, if you are flooded only for 1 hour, consequences will be minimum. If you are flooded, but if you have to stay in your house during 2 weeks, this is completely different because you need food, you need energy, you need water, obviously. And so you may define those things. If now you bring people who have been affected or people who are communities, you work with them in order to define what are the different marks they will have. They will characterize the situation where they are. You may give for each individual houses, according to a very specific situation, an index, which is providing an information about the current situation. And from that, you can introduce changes, improvement, reducing the flooding, less water, longer, and so on. And you can see how it's affecting their life and how index will change and will reflect the situation. So this is a type of things which has been made already by some colleagues. And of course, you can address various dimensions. I would like just to use the case of Nice. This is an aerial picture, so which is a high resolution. For those who have been on the French Riviera, you have enjoyed the Baie des Anges, the nice beach. We are in a place where we have a lot of buildings, historical buildings. So here you can see in gray all the buildings. And from those buildings, you can easily go and try to define what are the different functions of those buildings. You know, each building is now characterized. The red ones are governance, city hall, police station, and so on. You get transport, you get health. The green ones are for health, hospital, and so on, so which are potentially those which are useful in case of major crisis. Now it means we get a view about the main functions, about the main services. We know how it's operating and how it works. On top of that, we may have flooding. I told you we have sometimes very intense rainfall events, so this one is just, I would say, the 50 years return period flooding for the city of Nice. Yes, it's quite serious. I mean, so the deep blue over there, it's about 1.5 meters water within the street, so it's quite serious. It doesn't last so much. It's only a few hours, 3-4 hours maximum. But in that case, we have velocity which are higher than 3 meters within the street, so it means even with less than 15 centimeters, you cannot cross the street. Okay? So this is extremely dangerous, and it has to be carefully managed. So from that, and from the previous one, you can create this map. So this map is just showing the resilience index, so how each building is affected and how the population inside is affected by the flooding and how they can be and how they can live. So this one is just for the full city, and this one is just for in each individual building. Okay, so we have this information. Of course, there is assumption regarding the use of the building and so on, but roughly it works, and this is something which is used by the municipality currently in Nice. This is used also in Bangladesh. This is used also in China, in Spain, in Germany. So we are developing this approach in order to support the decision makers and the city services in order to manage the crisis. If you try to improve a bit the things, of course, there is a lot of work which has been made up to now at the building scale. This is an example, so which is from UK, from our colleagues. The DFRA agency has produced a lot of recommendation guidelines, how to protect yourself regarding flooding. It works, it's nice, but this is not a good scale. I mean, geographers will be happy. Working at the individual scale doesn't answer to the problem, because we have processes which are covering a wide extension. And so it means if you want to be operational, you have to cover a larger extension. And one of the extension you have to address is the block and the district for especially several reasons, because this is the scale for the networks. This is the scale for electricity. This is the scale for water. This is the scale for gas, and so on. So it means you have to address those things, and you can proceed in the same way and generate, once again, indexes not for each building, but for the block and for the district and for the city. And so with that, you may provide a global view that could be used by the decision makers, by the technician, at least to discuss and to identify priorities, how to move forward, and what could we choose in the different action we would like to push forward. The two things which have to be now push forward regarding the resilience. There is two, from my point of view, two main axes. The first one is to try to work on the structural measures, reviewing some of the design concepts we are still using since, I would say, 2 millennia, almost, trying to review those things. And on the other hand, try to work on the non-structural measures, try to better understand processes in order to improve preparedness and awareness. The first one is about concept, inherited concept. What you have over there is the city of Paris. You can see the organization of the city was very simple. You have a wall which is surrounding the city itself. And if you look at most of the city in France, but also in Europe, so this is the case in Germany, this is the case in Belgium or in Spain, you will see that the city centers was almost 5 to 6 kilometers for a very simple reason. It was just 1 hour walk from the west to east. If you look at the city of Paris, this is what you have. This one is Brussels. This is Europe capital. You will exactly see the same organization. So it means all the urban structures has been organized around this concept of center, which is around the 5 or 6 kilometers. You will say, okay, so what's the impact of the story? Currently, there is a huge impact, because if you look, for example, in London, this is the size of what has been created for the sewage system. And now we have a sewage system which is aging about 1.5 centuries, almost 2 centuries, which is in somehow governing the development of the city. You may have a very nice idea, but if you do not have the capacity to increase the sewage system, you will enter a very serious problem. How to manage the wastewater? In the same way, how do you organize the water supply for most of the city? So it means we have to break this approach and try to reorganize the concept. One of the concepts which was in the fact used before was the centralized approach. So we have to move to something which is decentralized. For energy grid people, this is something which is very familiar for you. And finally arrive to something which is distributed, maybe going to the scale of the block or of the district of the services we have to provide. So this is basically how we move on. This reference is quite old, 54 years, from a colleague from UK, which was working on the development of IT. So remember, 54 years for the development of IT networks. Everything is already written. We have already seen what is a paradigm to use. Obviously, we have to address a very different environment. So this is a case of new shape of cities. It doesn't fit with the historical ones. This is Los Angeles. This is Tokyo. Obviously, you have to integrate those new environments with new developments. The last point I would like to elaborate a little bit more is about knowing and acting on time. So right now, there is a technology which is allowing to improve the knowledge about the processes and especially to try to communicate and to support the decision. Communication networks are existing. Sensors revolution is on, so you get plenty of sensors which are extremely cheap that could be available to measures water condition, flooding, whatever you want, so it could be available. Most of the physical questions are solved, so we have the capacity to simulate and to produce elements. And we have now the possibility to integrate those tools in real time, so it means we will have the possibility to provide to the citizens, to the community, real-time information that could support the decision process. There is a lot of developments which are going on regarding smart cities, obviously. So this is also something which is coming up a lot in Europe and in Asia. And one of the key challenges is to succeed to integrate the various sources of data which are provided by the different utilities. And somehow this is a big challenge because for the current time, everyone is coming with his own solution, and it doesn't work. I can tell you, we are following this story since almost 15 years in the city of Nice, and it doesn't work. So finally, we came to something which is unified. We integrate all the data in one single storage environment, and we share those data, and we provide the services according to the profile of the users from the general public, but also to the decision makers. And what is changing currently is analytics, which is a capacity to provide intelligence on top of the data we are collecting. Right now, we are doing monitoring, but we will have the capacity to produce forecasts, to anticipate what will happen with various tools. I would like just to share with you some results and some illustration on those points. So this one, it's not a picture. It's a virtual environment for the city of Nice. It's a 3D with a resolution of 10 centimeters, which is one of the most accurate models we have in Europe. We have pictures about all the buildings, so it means you can walk in the street and look at the buildings around you in virtual reality. You see all of that. And the objective is to try to see how the city is affected by different situations. Could be heat wave, but could be also flooding. So this one is another view of the city, which has been affected by flooding. So what you have over there is the last strong event we had in 2015, in October 2015, and here you have a model which is showing how the city was flooded, and over there you have a simulation which is showing how the water was moving within the street. So we have the capacity to generate such a type of models everywhere, covering the full city and explaining to the population, this is a risk, it will happen that way, and you will be flooded during 5-10 minutes, or you will be flooded for 2 hours, and you will have 30 centimeters in your home, and so on. Tools are there, simulation engines are also there. So this one is another example which is just showing how accurate we can go. So this is almost all the drops arriving on the surface, and you see how those drops are going around. So it requests significant computation time. Don't worry, in few months, I would say, or a few years, we will have the capacity to do that almost in real time and to see in 30 or 40 seconds where the water is able to go. This one is just another example which has been just done with my colleagues. So we are computing on a catchment, so which is on the east coast of Corsica, so which is also part of France, where we are trying to simulate flash floods where we have to react in few minutes in order to protect the population. So here we are talking about 20 million cells. Models are representing the things, and about 6 hours of computation time in order to generate those things. So this one was just a model, and this one is produced in one environment which is more, I would say, user-friendly for the population that may understand how to react and how to adapt. Just to give you 2 additional examples. So this one is about urban flooding in Mexico. So even if in Mexico we do not have so much data, most of the data we may collect from remote sensing and different type of information may allow you to produce such a type of models, so, and to see how, for example, the airport of Mexico is strongly potentially exposed to such a type of event. And so this is really something which is matching what has been unfortunately observed. The last example I would like just to share with you an example in Vietnam, close to Da Nang city. The city of Da Nang is over there. So we have a huge catchment, which is about 10,000 square kilometers. Whoops, so I think it went just too fast. Yes, so. Okay, so I think it works, yes. So you have this very dense river networks, which is affected every year by some flooding, which is also useful for agriculture. So this is something which is used for the production of rice. And so we have been able to reproduce the flooding process, including for extreme situations, but we were also able to produce scenarios integrating climate change. And so what we have seen is, in fact, that this wet season has been shifted in the years. So it means the flood extent will not change so much. But the fact that this flooding season is shifted within the year, the rice production will decrease, because we may have only 2 production per year, as we have 3 production currently. So it means the consequences for the population could be quite strong. It's not the flooding itself, but that's the consequences on agriculture. The last slide, just to conclude and say, as it was said by Karen, so I'm also optimistic regarding the future. Resilience is an interesting concept if we take care to integrate and to have a proper definition. So the message is also for the engineers: be interested by the resilience and try to introduce this resilience in your daily practice and try to see how you can review some of the code currently used. And obviously try to develop the tools and the technology which is allowing to integrate those elements. And this is obviously an opportunity for developing cities. I mean, developing cities have the chance to cope with such environment and improving more faster than what we had in historical cities. Just before to say thank you, I would like also to thank my colleagues who have been contributing. I mean, models are nice, but it's hours or even months in front of the computers before to be sure to run with that. And I would like just to finish with this funny video, which was in Bangkok, showing the social resilience and adaptation. So it was during this big flood of 2011, and you can see that the kids was quite happy about creativity of his father and surviving to this big flood in Bangkok. Thank you very much.